So what I hope to do today is set the stage and put you in the world of systems biology a little bit, and to hopefully have you ready to go for both Jeff and Ed. And so what I've decided to start with is a brief definition of what systems biology is. And those of you who haven't visited the Institute of Systems Biology website, I highly advise you to. It's a great website, and it's actually a company that's been founded by Dr. Leroy Hood. So in his perspective, systems biology is the study of an organism viewed as an integrated and interactive networks of genes, proteins, and biochemical reactions, which gives rise to life. And this is crucial because often when you hear about systems biology, most of the databases and the tools that you can access are very limited to just, let's say, genes or just proteins. And what you really need to do is be able to have access to all flavors of our biochemical system. The terminology's been tossed around for quite some time, actually, all the way back to the 30s. And the first thing I have on my timeline here is a published book about individual growth model. And you'll see it, without going through every item, but you'll see that the flavor of this slide attributes systems biology to a lot of physics, a lot of math, and computer modeling. Dennis Noble, who's the person who developed the pacemaker, is considered the founder of the first computer-based biological model. And as you go through, we really start to see the emergence of systems biology in curricula, maybe around the 70s, commencing with different types of theories. So if you are interested in getting more details about the history, just feel free to contact me and I'll help you with that. Often, we assume that a systems biologist is a person who just works with computers. And as you maybe already with your careers, you've noticed that you probably are interacting with several different types of scientists. Collectively, we all become systems biologists, and by choice, or we almost have no choice but to be familiar with this field, no matter what you do. I'm a biochemist, and I never thought I'd be speaking at BioIT, so just to give you an idea. So do not limit yourself in thinking that just because you're not, let's say, a computer programmer, that you don't necessarily appreciate systems biology. And we work with clinicians and toxicologists and chemists, as well as mathematicians and statisticians, and everyone is really crucial to this. So this slide is, I think, a really good summary, and I pulled it out from a review a couple of years ago. But in order for us as individuals to be able to comprehend systems biology, there is a checklist that we should become familiar with. The first is we should be able to access a catalog of these biological and chemical entities that the definition alluded to. Not only that, we should be able to access a catalog of their known roles and relationships. Second, you have to have the ability to quantify this somehow. So we're all analytical, and we have to be able to tag a number to something because reviewers like that. So when you're thinking about accessing a tool or creating a database, keep that in mind. You also should be able to integrate different types of data. These days, there's proteomics, microRNAomics, there's all different flavors of it. So as a result, we need to be able to integrate these different forms of biology. Also, the tools that you access to use the information in these catalogs should be able to create some type of model. And this calls upon the computational and mathematical efforts of designers to create these models so that you can actually connect these components together. And lastly, it's only as good as your testing is. So you should be able to come back in with a problem, test it, validate it over and over again, and trust it.